Now let's look at matrix multiplication. We want to multiply matrix A, which is 1, 2, 3, 4, 5, 6, with matrix B, which is 1, 2, 3, 4, 5, 6. So we put these two together, and the way we multiply them is row and column. So this row here will multiply this column, and this row will multiply this column. And then we move down to the next row. This row will multiply this column, and this row will multiply this column. And we get the results, and we place them in this position here, and then this position, and this position, and then in this position. So let's just talk through the very first one here. So we're going to have 1 times 1, and then we're going to add on 2 times 3, and then we're going to add on 3 times 5. So we're going to have, for the 3 times 5 is going to be 15 plus the 6, which is 21, plus the 1 times 1, which is 1. So that's 22 altogether. So this row times this column is a value of 22, and it gets placed in the first position. Now I've changed this straight into hex because that's what we're going to have in our computer. So the number 22 in hex is 16. Now to get the next one here, we're going to multiply the 1 and the 2, and then add on the 2 times the 4, and add on the 3 times the 6, and this gives us 1c in hex. I'll just talk through the last two here and that'll be us done. So the next ones are going to be 4 times 1, 5 times 3, and 6 times 5. And when we add those up together, we get 3, 1 in hex. Now finally, we're going to have the 4 times the 2, plus the 5 times the 4, and the 6 times the 6. And that gives us 4, 0 in hex. So our final answer is this matrix here. And you see I've put a little h next to it just to tell us it's actually in hexadecimal. Now, a nice little neat trick to remember here is that whenever you're multiplying these matrices together, you can only multiply certain matrices for it to make sense. So in this instance here, we've got a 2 by 3 matrix that's got 2 rows and 3 columns. In this instance here, we've got a 3 by 2 matrix, that is 3 rows and 2 columns. So if we write this 2 by 3 and 3 by 2 side by side, then we can say that the final answer is going to be the 2 by 2, and we can only multiply them if these two numbers are the same. That is, if the number of columns in this matrix here is equal to the number of rows in this matrix, then we can multiply them together. If these numbers are different, we can't form the multiplication. So a lot of the time you'll see these written side by side, and you'll just kind of cross this out, and what's left over is a 2 by 2 matrix, and that's the final matrix here, which is a 2 by 2. So now we've seen matrix multiplication and how we do it, well, we actually want to be able to model this in our assembly language. Now, it's going to be quite difficult to do that with the matrices in the form that they are in. The reason why it's going to be awkward is that we're going to have to get to each of these values here in the right order. And we can actually do that much easier if we were to take the second matrix here and transpose it. So I've done that down below, and you'll be able to see down below why this makes it a bit easier. So we leave the first matrix A as it is, we transpose the second matrix. Now remember, when we transposed, we swapped the rows and the columns. So the first column here becomes the first row. The second column here becomes the second row. So this is now going to run 1, 3, 5, 2, 4 and 6. So it means that it's much easier to get at the values here, because remember all our values are just in an order, just one after the other. So it means that whenever we put it in this format here, each of these values we can say is contiguous. That is, that in order to, say for instance, to get this first term here, then what we did up here, we multiplied the 1 by the 1, and then the 2 by the 3, and the 3 by the 5. But now what we can do is we can multiply the 1 by the 1, the 2 by the 3, and the 3 by 5. And you can see here that it's much easier to multiply these because they're in the same positions within the matrices. So whenever we multiply this row here, we can multiply it just with this row and get the value 1, 6. And then what we can do is we can go back to the beginning here and we can allow this one to continue, and we can multiply 1 by the 2, 2 by the 4, and 3 by the 6, which will give us the 1a. And then what we can do is we can take this back to the beginning again, so we go back to the number 1, and then we can make this jump to the next row. So when we jump to the next row, we'll have 4 times the 1, 5 times the 3, and 6 times the 5. And then we can make this one jump back to the beginning, and then this one here can jump on to the next row. So we'll have 4 times the 2, 5 times the 4, and 6 times the 6, which will give us the value of 40. So it's much easier for us to write the code to generate this matrix multiplication whenever we transpose the second matrix. And this is a common method of simplifying the code for this type of matrix manipulation. So let's go ahead and we will see this within our assembly language. The code for matrix multiplication is more complicated than previous code that we have seen. So I don't want to talk over each and every line, but I will give you a flavour for how it works, and again you will have access to it within the resources section, and you can go through it one line at a time using the CPU. So we've got the calling function on the right and the subroutine on the left, so we'll go over the calling function quickly. So we're going to have two matrices, so we've got matrix A. In this instance here it's a 2 by 3, so it's 1, 2, 3, 4, 5, 6, and we have to tell it the length of this matrix, the rows is 2 and the columns is 3, so it's a 2 by 3. We then give it the second matrix. This second matrix is going to be a 3 by 2, so it's going to be 1, 2, 3, 4, 5, 6, and we tell it here it's a 3 by 2. We also have to tell it what the output matrix size is going to be. So the output matrix size here is going to be a 4. And you can see that quite quickly if you say 2 by 3, 3 by 2. So the 3's cancel and we're left with a 2 by 2. Now I could have added this into the actual subroutine and we could generate that within the subroutine, but I've left it here for the moment. Now the final output again is going to be a matrix which is 2 by 2. So that's got the 2 by 2 here. So we're going to push the address of matrix A, the value for the row and columns MA and NA. We're going to push the address for matrix B and the values for the rows and column. And then we're going to push the address for matrix C and the address for the rows and columns for matrix C. So we push all of those values onto the stack, we jump to the subroutine, we get into the subroutine here in the left hand side, it runs through and generates the values and it saves the values into the matrix underscore C at these points here, so the DS sets aside the 4 memory locations. And that's it finished, and it just ends the program. So that's the calling function. Let's go on and we will look at the actual subroutine. Now the subroutine is more complicated, and you can see here it's got 177 lines, including all the spaces. So I can give you a flavour of how this works. Now again, we go through our usual process of housekeeping. So we take all of the original register values, stick them into memory. We then pop all the values off, so we can see we're popping off the return address, the value for our position for the length of the C matrix, which is NCMC, and the actual position for the memory locations for the matrix C. We do the same for the B, and we do the same for the A. Now, the way I work the code is that we could have the potential where we might have just a single value matrix. So for example, just matrix 5 times matrix 5. And the answer to this would just be a single value of 25. So the code as it was written didn't cater for this one possibility. So I've just added this possibility in as a special case. Okay, so this little part here just generates the value for this if it's a 1 by 1 and a 1 by 1. So it just basically adds these 4 numbers up. If it finds the numbers a value of 4, it knows it's just a single value matrix and multiplying a single value matrix. And you can see here it jumps down to a line called single. So basically it misses out the entire lot of code. We don't really need to do very much. So we head right down to the very bottom to single, and what we do here is we take the values for the matrix and we multiply both of them together. So in effect this multiplies the 5 with the 5, and then we store it at the correct position here, which is in the matrix C output, and then it just goes to the end of the program, so that's return, and then it just it will take all the values out of the memory back into the registers just as part of our housekeeping, and then it will return to the start address. Okay, now that's if it was that one special case, and as I said, I'm not going to talk over all of the lines of code. What you can do is you can read the comments and you can work through it as part of the actual loading it up into the CPU, and you can test it out for yourself and you can see how it all works. Now, if that wasn't the case and we don't have this particular value here for just a 1 by 1 matrix multiplying a 1 by 1, then we can have any other possibilities. When I say any other possibilities, as long as they meet the requirement that the column of A is equal to the number of rows for B. Okay, so and again, it doesn't check for that. It assumes that you know that that's the case. It wouldn't be difficult for us to put a little trap in, and that's always a possibility. And if you decide you might want something like that yourself, you could add a trap in where it tests the column and rows and make sure that they are actually the same. And if they aren't, then it'll come up with a trap and it'll say you can't multiply these matrices together. It's something I may well add in later on, and if you want to, again, you could add it in yourself. So let's say, for example, we have a matrix, it's of the right order and we can multiply it. Then we're going to go through an initial set here, which is, again, it's just a little bit of housekeeping. We're going to take a few values out that we need in order to go through the loops. Okay, so we generate these values here, and there's one called MA count and one called NB count. And again, we work out the lengths, so we can work out the overall length of matrix A just by multiplying the row and the column, and the length of matrix B by multiplying the row and the column. And then the interesting thing here is that we now have to go through and transpose the matrix B. So in order to transpose it, you've seen in the last video, we generated the transposition subroutine. So we are able to call that transposition subroutine, and I've done that here. So we push the matrix B, we push the length, and then we push the row and column count, and then we push where we want to store the row and column count for the return matrix, and also where we want to store the actual transposed matrix values. And then we jump into that subroutine, and I'm not going to open up that subroutine just now because you've seen it in the last video, but it jumps into that subroutine and it forms the transposition of matrix B, and then it returns back out to this very line here, and then we're ready to go again. And this is the beauty of generating these subroutines and getting them right and getting them working, because you can just go and call them, and I don't need to bother about the transposition and how it works. And after we've watched this video, you won't have to bother about how it generates the multiplication. You can just call it, and as long as you know you're pushing the values in the right order into the subroutine, you know you're going to get the results that you want. So once the transposition has been generated, we're going to in fact have 3 loops here. So again, this is just a kind of general description of it, but I'll go in here and I'll show you. So we're going to have an inner loop here, okay, and then we're going to have the outer loop, and then we're going to have a master loop. So apologies if you don't like the names, you can always rewrite it yourself and put better names in. So in effect what we've got is a triple nested loop. So, and the reason why we've got a triple nested loop, if we head back up and we'll have a look, see if I can get this into a position where you can see it. Okay, so the reason why we need a triple nested loop is that first of all, we're going to have to multiply the 1 and the 1. So once we multiply the 1 and the 1, we're going to have to go back to the beginning again and multiply the 2 and the 3. And then we're going to have to go back up to the beginning again and multiply the 3 and the 5. So in effect, that's the inner loop that produces the number, okay, which in fact would produce the number 16. And then we're going to have to go back to the beginning again, and then we're going to have to go to the outer loop. So the outer loop is going to tell it to go back to the beginning here, but continue with the next 3 here. So the outer loop says go back to the beginning and go to the inner loop again, and again loop round about. So we loop round about 1 and 2, 2 and 4, 3 and 6, which gives us the value of 1a. So now that we've worked through the inner loop and the outer loop to go for the multiplication of this 1, 2, 3, 1, 3, 5, 1, 2, 3, 2, 4, 6, we're then going to have to go through the same process, but we're going to have to go through the same process with the next row here. So at this point here, it goes to the master loop, and the master loop jumps into this position here, and then it resets this back to the value of 1. And again, we go to the inner loop and we multiply 4, 1, 5, 3, 6 and 5. And then we go to the outer loop to jump down to the next one again. So when we jump down to the next one, we do the 4, 2, 5, 4, 6 and 6, which gives us the 4, 0. So then we've worked through this row, and it jumps back up to at the end of that, it jumps back to the outer loop. The outer loop will have gone to 0, and then because it's gone to 0, it will then jump to the master loop. and the master loop at that point will have looped through these two rows. The master loop will have gone to 0 as well. So it means that the outer loop and the master loop will have gone to 0 and it will have finished. Okay, so that's the basic setup for the looping structure, and that's why we've got a triple nested loop. So again, I'm not going to talk through the triple nested loop here, but that's the basic premise of the code. So the inner loop here, and then the outer loop and the master loop. And the difficulty in it is just setting up the count values and ensuring that the count values are at the right positions, and also to reset the count values whenever you jump to, say, the outer loop or the master loop. So it's a typical kind of bit of programming that you would see for a triple nested loop, and just ensuring you get the count values running properly. Okay, so that's the long and short of the program, and that's the coding. And again, whenever it's finished, it will jump at the end here. If you come up here, when the master loop has finished, it'll jump to return. So that's jump of equal to return. So I'll head down to the return line, and it will then just replace or restore the values for the registers, and it will jump to the return address. So it jumps back to the calling function. So that's the basic premise of the code. You can always take it, load it into the machine, and you can run through an example one single clock pulse at a time. Okay, so let's go ahead and we'll see it running on the machine. I have loaded the subroutine into the ROM and the program into the RAM, and you can see I've actually started it running. Now there won't be anything to see here for the first few seconds, because all it's doing is loading all of the values for the matrices into the memory locations. So it's not doing anything here with the registers. If we were to open up the RAM just now, you would see the values being placed in the memory positions. So if we give it a few seconds here, you can see it's starting to run up these values. So it's going to get the lengths. 2 times 3 is 6, and the 3 times 2 is 6, because it's a 2 by 3 and a 3 by 2. So the length for both of them is actually 6. So it generates these values, and then after it's generated these values, it's going to go in to the subroutine and do the transposition. So you'll see the positions values here for so that's 1, 3, and 5, and the other ones will be 2, 4, and 6. That's 2, 4, and 6. So that's it transposed matrix B. So now it's transposed it, it will be able to get through the multiplications, and you'll see the values appearing here. So that's the first value, 1, 6. The next value we're going to get is the 1C. And then it has to jump to the master loop and then back into the inner loop, and it'll get the other two. So the other two are 3, 1. So that's in here. And the final one is going to work out here is the value 4, 0. So that's 4, 0. So that's it, worked out all of the 4 values, and it's going to replace all of these registers back to their original values, which were all zeros. And you can see that's it finished. So let's go ahead here and we'll stop this, and we will go in and have a look within the actual RAM. So again, it's a little bit small here, but hopefully you can see it. So we're going to start off with the original value for our matrix. So the first matrix A is going to be 1, 2, 3, and then the next row is 4, 5, 6. So I'll go with that again. It's going to be 1, 2, 3, and then the next row is 4, 5, 6. And the next two positions here are telling us it's a 2 by 3 matrix. And then matrix B is going to be 1, 2, 3, 4, 5, 6. And this is a 3 by 2 matrix. And then the final answer is going to be the value of 1, 6, and then it's 001C, and then it's the 3, 1, and then it's a 4, 0. And the length, the row and column for this is going to be 2 by 2. So that's worked out, and it's worked out quite well. Now I have ran this with just a single values, so for example 2 single matrices of value say 5 and 5, and it'll give you the value 25, and it'll tell you it's a 1 by 1. And I've tried it with, say, multiplying lots of different matrices, and I actually have done it with an 8 by 3 multiplying a 3 by an 8. So that'll give us an 8 by 8 matrix. So it'll give us 64 different values, and it's worked through the entire matrix multiplication in about 5 minutes or so. Now, one other thing to note here is that I have maximized the number of the output that you can generate. So the maximum matrix size you can generate is an 8 by 8. But if we wanted to, we could extend that just by a simple change of the code, with just one value in the code, to say a 16 by 16 matrix, which would be 256 values. But I think for the moment an 8 by 8 matrix output with 64 values is fine for us just to work with. So that's us finished pretty much with our matrices. If there's anything else, we can add it in at the end, but there won't be anything that's more complicated than this multiplication. What we really want to move on to next is to get away from the vectors and the matrices, and we will move on to looking at complex numbers. But again, complex numbers are going to be generated in a similar way for the matrices and the vectors. We're still going to use the basic array structure. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.